Hello everyone. In this video we are going to talk about particle kinetics using the path coordinate, or what you might call normal, tangential, binormal coordinates. So here we have a car going on an exit ramp with a radius of curvature of 60 meters. The mu-s between the road and the tire is 0.4, and the rope is also, the ramp is given a slope of beta degrees. You want to find what is the minimum beta needed in order for the car not to lose any traction and basically slip sideways. So the first step is definitely free body diagram. So the forces that we have on this car are mg, which is downward, a normal from the surface to the car. Let me see if I can use a straight line here. So that's n, that is mg, and then we have friction. Now the friction in general on a car has two components. One of them is longitudinal, which is along the direction of motion, and that is when you want to accelerate or decelerate. In this case, we assume that the car is exiting the ramp at a constant speed. Okay, although it's going to be the maximum it can, but still the car is going to maintain that speed constant. When you don't change that component of the velocity, the speed component, right? You just change the direction, not the magnitude. You do not need a longitudinal friction. So that is going to be in the t direction, and in the t direction there is no v dot component, a change in the speed, so there is no longitudinal friction needed. However, if there is no lateral friction, the friction also has a lateral component toward the center, and if that one does not exist, the car will not get the centripetal acceleration needed to go around the circle. If that component is not there, the car is going to basically move on the direction of this tangent line and will be going into the grass area, right? It is not capable of going along the arc. So there is a lateral friction here, and that is tangent to the road. So it is going to be like this. Let me move it up a little bit, something like that. Yes, and this one is F. So these are the three forces. Clearly the angle between N and mg is the same as the angle of the slope, so this angle is also beta. Now here we use the NTB coordinate, where N is toward the center of rotation. So when this car is on the slope, actually it is rotating about this vertical axis. So the center of rotation is on this axis. So basically N axis is going to be from the centroid toward this axis. Okay, so this guy here is your N axis. So we can call it En. Et is along the direction of motion, so Et is like this in this top view picture. In this front view picture, Et is going to be perpendicular to the board toward us, okay? So if we want to draw Et here, Et is out of the board toward us, that's Et. And EB is Et cross En, which based on the direction of Et and En, it has to be downwards. So EB, the binormal direction, is going to be like this. Okay, let's see if I can improve it. There we go. So this is EB, right? So these are the unit vectors or the coordinate system and the forces. Now that we have the coordinate system established and the forces, we write down the governing equations. So we have three axes. It's a particle, so we have three equations of motion. Some forces along t direction, which in this case there is no force along t direction, is 0. That is equal to mat, and if you remember, at is dv over dt, the change in magnitude of the velocity, the change in speed. Right? Since there is no change in the speed, there is no friction. Clearly, so this comes from the fact that v is constant, correct? Remember, this v here is constant. And so dv over dt is 0. So 0 equals 0, of course. It doesn't give us anything, but you see clearly it is working. In the n direction, if you can see in the n direction, we have basically a component of n and a component of f. So n has the sine component, and that is positive. So it is going to be n times sine of beta, and then plus f times cosine of beta. This is equal to m times an, and an is v squared over rho. In the binormal direction, we have mg positive because b is downward, then plus f times sine of beta, that one is also down, and then minus n times cosine of beta, which is upward. This is equal to mab, and AB means the car is going up and down the ramp, which is not happening, so that one is 0 as well, and so you will get a 0. And so the first equation is not going anywhere, so we don't need that. I would call this equation number 1, and I would call this equation number 2. Now, what the problem is asking is to find beta as a function of v, but it wants the maximum v possible. So you want to make this Vmax, right? And so the problem is asking what is beta as a function of Vmax and mus and rho, okay? The numbers that are given. What about mass? We'll see the mass would cancel out. We don't, beta is not going to depend on mass. So this is the unknown of the problem. Now here I have two equations. Do I have enough equations for the unknowns? Let's find the unknowns first. So I have n to be unknown, f is an unknown, Vmax is an unknown, and beta is an unknown. So there are 4 unknowns. But since I need to find one as a function of the other and not find all of them as a separate number, I really cannot say beta and Vmax are both unknown, because if Vmax is a given parameter, then beta is the unknown. So Vmax should not really be counted as an unknown, okay? So Vmax is a given parameter as well as mus and rho. So I have 3 unknowns here, n, f, and beta, still not enough. I need one more equation. And that comes from the fact that when you want to exit the ramp at the maximum speed, that means your centripetal acceleration, Vmax over rho, is going to be max. And if you look here, for that to happen, you really need your friction, which is the major component providing the acceleration in the n direction, to be max. So you have to have maximum friction so that you can exit at maximum speed. So this f has to be f what? F max. And if you remember, we said that this friction is a static friction. There is no lateral sliding. So this is a friction which is static, and the friction max static is what? As you know, it is when you're about to slide, and that is mus times n. So clearly f is not a separate unknown, it does depend on n, so I can really consider f to be depending on another unknown. So now you have two unknowns, beta and n, and two equations, and that is enough to solve for everything. Right? So the first thing I do, I plug in 3 into 1 and 2 to get rid of that friction term. So if I plug it into 1 and I factor out n on the left side, I will get n times sine of beta, and then plus mu s times cosine of beta is equal to m Vmax squared over rho. And I can call this equation number 4, and then if I plug in 3 into 2, then again factor out n on the left side, I will get n times sine of beta times mu s, then minus cosine of beta, and I take mg to the right hand side, so I will get negative mg, and that is going to be equation 5. And now to eliminate n between 4 and 5, all I need is to divide the two equations, right? Because if you do, not only n goes away, m goes away, which is a parameter that is not even given. So here I'm going to divide 4 by 5, and that will give me this relation, that sine of beta plus mu s times cosine of beta divided by mu s sine beta minus cosine beta is going to be negative Vmax squared over rho g. Okay, so now here, before I find beta as a function of Vmax, mu s, and rho, I would like to take a look at what happens for different beta angles. If I have mu s as the number given here, 0.4, and rho to be 60, what is going to be the value calculated for Vmax? Okay, so what's going to happen to Vmax if I change beta from 0 to, let's say, for example, 15 degrees, 20 degrees or so, correct? So first, I would like to do a plot on that and find out why is it that they add an angle, a slope to the rope on the exit ramps or entry ramps. What's the benefit of that? And then we'll find beta as a function of Vmax, and then we look at the effect of Vmax on beta, like the backwards function, the inverse function. So clearly from here, if I want to solve for Vmax, Vmax is going to be the square root of, so I multiply the left hand side by rho g and provide the negative on the left side, which will negate the denominator. And if I do that, it is going to be rho g times sine beta plus mu s cosine beta, and then it's going to be cosine beta minus mu s sine beta. Okay, so this is Vmax as a function of beta, rho, and mu s. So first, let's look at the plot for that. Okay, so this is the function, rho times g, right, times sine beta plus mu s cosine beta divided by cosine beta minus mu s sine beta, right? And then the power 1/2 is the square root. So mu s and rho are given, and I changed my angle from 0 degrees to 15 degrees, 1 degree at a time, and since they are in degrees, I use sine and cosine d. I do the plot, and if you do that, here is the result, which you clearly see, like my Vmax without any without any angle, when beta is 0, the max speed that I can exit is 15.34, right? If you want, I can convert them into miles an hour, so you have a better, so these are in meters per second, so I can basically multiply them by 3.6 to get kilometers per hour, and then divide it by 1.609, which is each mile in kilometers, right? Now, if you do it, you might get a better feeling about the numbers. So the number that I can exit is a little bit more than 34 miles an hour without a slope, but as I go to 15-degree slope, now I can exit with about 47 miles. So instead of 34, I go to 47. And you clearly see the more angle I apply, the faster I can exit. So the angle here, the slope, is there to help you what? To help you basically exit the ramp. And let's say if you say, well, the maximum exit on the ramp is let's say 40 miles an hour. So for 40 miles an hour, you need something like let's see, what number is this? Yes, somewhere between 6 and 7 degrees, right? So with 6 and 7 degrees, you can exit 40 miles an hour with a friction of 0.4. But when it's raining and the road is slippery and mu-s is smaller, let's say mu-s now drops to 2. Now what happens? For the same road, if you do that, now you see, first of all, I can never get to 40. 40 is too much. But if I get 15 degrees slope, right, I can exit at about 38. So definitely I need to bring my maximum speed of the exit on the ramp smaller, depending on how much mu goes down in a rainy day, right? But let's say it doesn't go as bad as to any 0.2, it goes to 0.25 maybe. So now, you see, if I want to still maintain that 40, I need 14 degrees slope. So without a slope, the best I can do is 27, but with 14 degrees slope, I can still maintain the 40 miles an hour. So definitely the slope is helping to bump up the maximum exit speed of the ramp. So you see the effect of that. Now from here, I want to find actually the other function, beta, as a function of Vmax. So what I can do here is to cross multiply both sides, right? Which if you do and get rid of the negative, you will get Vmax squared times cosine of beta minus mu s sine beta is equal to rho g times sine beta plus mu s cosine beta. And here you bring all the sines to one side, all the cosines on the other side. If you do so, on this side you will have cosine of beta, and this is going to be Vmax squared and minus rho g mu s. On that side you will have sine of beta, that is going to be rho g plus mu s times Vmax squared. And if you divide both sides by cosine, you will get tangent of beta, and if you get arctangent, your beta is going to be tangent inverse of this term divided by this term. Oh. And this is your final answer. Beta as a function of, or beta minimum as a function of Vmax, rho, and g, and we can plot that one as well in MATLAB. Here is this function here. I wrote it. I changed my Vmax from 15 to 35. We don't really need to go to 0 Vmax, right? It's a big number typically. And here I plotted again Vmax in miles an hour versus beta. And if you do so, you'll see that basically my beta that I need for some Vmax is increasing. So as I want to exit the ramp faster, I need to bump up my angle faster here. And here these numbers are in radians because it's arctangent. If I want them in degrees, I have to do it in arctangent d. So now maybe this is more reasonable, right? So if you are below, let's say 30 something, 33, 34, you don't need an angle. But as you are going to faster and faster exiting the ramp, right? So if you want to exit the ramp at 50, then you need something like 17 degrees slope, right? So that's why, for example, if they limit the maximum exit speed of the ramp to, let's say, 45, right? Don't go faster than 45 on this ramp, then they know that based on the mu-s they have between the tires and the road, they need at least 12 degrees, right? 12.5 degrees of slope to make it happen. Okay, so hopefully this problem with the explanation of it and everything was useful to you, and you learned something about why they give slopes to the entry or exit ramps on the highways. Thank you so much. See you in my next lecture.